Howdy Square Battlers! In this video, we'll be taking a more detailed look at how to implement the logic for your square, along with a few ideas or strategies to get you started. In case you haven't seen the other quick introduction video, you can get started with a SquareBattle team by first installing the SquareBattle package in VI Package Manager. VI Package Manager, VIPM for short, is shown here on the right with the package already installed. With the package installed, a new project template will be available in LabVIEW that creates everything needed to start a team. When creating a project, you will be able to enter the project name, which will automatically be set up as the team name, but the team name can also be changed later. Once the project is ready, the first thing to check out is the README, which includes reminders of how to get started. The main tool for keeping track of where to put logic is the Bookmark Manager, which lists the optional and required locations to fill in your logic. Everything you can edit will be in your team project library under the LVLib file. Everything else in the project is there to enable testing your team and should not be edited. Any edits made to any files outside of your team library may break compatibility with the SquareBattle engine when you upload your submission. Once your team is ready to submit, you can create the zip file by running the build specification in the project to create a single file that can be shared with other teams for testing and to upload to the submission website. This zip file includes only the code for your team, which is why it is important that nothing is changed in the game engine. The last interesting item in the project besides your team is the SquareBattle launcher that runs the GUI and lets you run battles between teams. Let's see what actions are available for a square to take and how it specifies them by looking at the square's run VI. On the block diagram, you'll see a few diagram disable structures containing all of the sub-VIs you can call from the square that provide information about the game or provide helpful utilities that are common for square logic. The main task for a square's run VI is to decide how to populate the run result cluster that is an output of this VI. This cluster tells the game engine to take one of four actions: wait, move, attack, or replicate, and what direction to perform the action in. Additionally, when replicating, the square must provide the new square instance that will be added to the game. In SquareBattle, the coordinate frame is arranged such that the origin, 0, 0, is in the bottom left of the grid, and rows and columns increase up and to the right, respectively, just like quadrant 1 of a Cartesian coordinate frame. Unlike the normal Cartesian plane, in this game angles increase in a clockwise direction, starting from east. Each round, game logic is run in the following order. First, each square that is able to perform an action has its run VI called to collect the run result value. Next, moves and replications are handled. Any squares that end up in the same position as other squares after moving and replicating are eliminated due to collisions. Lastly, attacks are processed and any square that is present in a location that was attacked is killed. Since attacks are effectively processed all at once, two squares that attack each other will both be eliminated. Moves and replications are processed before attacks, which means that a square can move into an attacked position, though it has no way of knowing ahead of time, and will be killed. And the game engine does not prevent friendly fire or same-team collisions. It is up to you to implement the logic that ensures your own squares do not collide with each other or move into a position that is being attacked by a friendly square. With the rules behind us, it's finally time to explore implementing square logic. I'm going to start by moving the disable structures out of the way, but make sure they're still easily available. Since the primary purpose of the run VI is to specify an action to take, let's look at the action helper sub-VIs first. These sub-VIs only require the necessary inputs for the intended action and should get wired out to the run result indicator. It doesn't get any simpler than waiting, which needs no inputs and results in no action for the square for the round. Next is move, which only requires the direction that the square should move. Directions are specified using a type-deft enumeration of the 8 possible directions. Then we have replicate to grow your active square count. It takes a direction that the new square should be placed relative to the current square, as well as the square instance to use for the new square. It's common for squares to simply create a copy of the source square, but it's also possible to run some configuration for the square to create, as well as create additional square classes to encapsulate different behaviors within the same team. It's also possible to implement different behaviors with K-structures in a single class, so choose whichever route you're more comfortable with. The last action, attack, only requires a direction input, and if a square ends up in that location at the end of the round, it will be eliminated. The last of the action sub-VIs is the wait if occupied sub-VI. This makes it easy to perform a move or replicate if the adjacent space is unoccupied, and will instead result in a wait if it is already occupied. Since this works with multiple actions, the action to take if the position is open needs to be specified. The game field info sub-VIs are critical for letting your square know what's around it. First is direction status, which given a single direction, makes it easy to know if the position is currently empty, contains a friendly square, or contains an enemy square. It also provides the index of the team occupying the square, or -1 if it's empty. This can help differentiate teams or your own squares. Your logic should stick to using the booleans and the other utility VIs instead of the team index so that joining multiple teams into friendly groups will be possible. Using the VI is as simple as wiring the square input, specifying the direction, and then using an unbundle by name to check to see if that direction is empty, has a friendly, or an enemy. The next three sub-VIs respectively return all directions that are empty, contain enemies, or contain friends. These three sub-VIs return an array of directions that can be chosen from for moving or replicating to, attacking an enemy, or making sure a friendly square isn't collided with. Keep in mind that even though a square might be currently empty, it is possible that another square also tries moving to that location, which will result in being eliminated due to collision. Knowing if there are enemies around the square is crucial because it is very likely they'll be attacking your square. You can try strategies such as running in the opposite direction to maintain your population, attacking the enemy and you'll likely both be eliminated, or keep track of where enemies have been seen to create even crazier strategies. The last of the game info VIs is to get the team index of all neighbors at once. The positions in the array correspond to the values of the direction enumeration. Again, in most cases you will want to stick to the VIs that tell you empty, friend, or enemy, but this VI does enable some more capabilities for advanced strategies. I'm going to skip over the other utility VIs, as we're about to use a few of them, and they all have documentation that shows up in context help. For this first implementation, I'm going to show off a way to have squares move in coordinated directions. If all squares try to move in the same direction, it's significantly less likely that they will collide with each other. This trick relies on performing some modulo math on the round number. First, the current round number is attained by using the round number game status sub-VI. The round number is integer divided by the number of rounds a square should travel in a straight line. Then the remainder of dividing by the number of possible directions is taken, which can be coerced into a direction enumeration value. This modulus, or remainder, will generate a value that continuously repeats from 0 to 7, which is the numeric values of the enumeration. All that's needed to get from the numeric value to the enumeration value is a coerce to type node. With this little bit of math, we can watch this work for a single square by using the direction to generate move actions. We can see the effect more easily by making the direction change more frequently, let's say every 5 rounds. Before I run the GUI, I want to add some indicators to the code so we can see the results of each step of the math. SquareBattle is set up to be easy to debug with non-reentrant VIs for all team implementations. While a match is running, you can leave your Run VI open to watch updates for any indicators you've created, as well as probe wires on the block diagram. The indicators I'm adding here will allow us to see the round number, the result of the division, the remainder of dividing that by 8, and the coerced direction, so I can be sure everything works as expected. It's always a good idea to have descriptive labels for indicators, so I'll go ahead and rename these as well. Now with these indicators on the front panel, let's launch the SquareBattle GUI and watch it run. First, my team needs to be added to the match. Note that SquareBattle always stops a match when only one active team remains, so I'll only be able to single step this single square. With the first round run, the round number indicator on the run VI is at 1, and we can see the results of the rest of the maths. However, because of the division, nothing else has changed yet, so I'll step a few more rounds. Every 5th round, the square changes what direction it is moving, and will eventually trace out an octagon. With this demo of a simple movement strategy done, let's explore how to use the team class to share information across all of the team's squares. I'll start by removing the existing logic, as I'll be creating different movement rules for this new implementation. To understand how this can be accomplished, let's look at the VIs that already exist in the team class. Much like the squares run VI, there are VIs that get called at specific times in a match. Start game can contain logic for setting initial values at the start of a match, and endgame is where any dynamic resources created in start game should be cleaned up. Since information can be stored in the team class, which is passed to all squares in a team, other mechanisms for sharing data between squares are not needed, as was the case within Digit's SquareBattle implementation. Then there's the new round VI, which the engine calls at the start of every round. This is useful to reset data that helps make decisions for a single round. One of the first things that is needed is to have the team store the board size that's passed into start game, so different data structures can be sized correctly. I'll accomplish this by adding a numeric to the class private data cluster that can be set in start game. With the size numeric now in the class private data, a bundle by name can be used to save the value passed into the sub-VI in the class data. This allows the board size to be used in all other team VIs by unbundling the size from the class wire. The board size will allow me to create a two-dimensional Boolean array to keep track of where squares are moving or replicating to, so that multiple squares don't try moving or replicating to the same location. I started by initializing this array in the new round VI, but realized later that I needed to move it to start game for the strategy I was making. So if you're following along, you can wait until I realize my mistake. In SquareBattle, matches always take place on a square board, so the single size value is used for both dimension sizes. After a bit of straightening up, this array will also need to be stored in the class data, so I'll create an indicator that I can cut and paste into the class private data cluster. I also changed to a smaller Boolean element, which is nice if you want to create a large array on a front panel that lets you visualize the map. Then, just like the board size in start game, a bundle by name is used to store the newly initialized Boolean array. With the unsafe position array available in the class data, the array can be checked and manipulated from the square's run VI, but not directly. To work with the array data stored in the team class from the square class, sub-VIs need to be added to the team class that the square's VI can call. This is accomplished by right-clicking the team class in the project and selecting New, VI from Static Dispatch Template. It's always a good idea to make sure VIs are recognizable, so I'll go ahead and customize the new VI's icon first. This VI will be used to simultaneously check and mark a position. To be able to specify the position to check, I'll use the position type definition that exists in the SquareBattle library. This could also be copied from one of the utility sub-VIs that has position as a terminal. With the control placed, I'll wire it up to the connector pane of the sub-VI so callers can pass in the position value. I also need to save this VI. This VI should let the caller know if a position is safe to move or replicate to as far as the team knows, so I'm adding a Boolean indicator that can return the safety of the position to the caller. With the input and output taken care of, I can work on the logic for this VI. As usual, I'll practice a bit of block diagram feng shui first, and then I'll use an in-place element structure to access the array in the class. The in-place element structure can have named bundlers added to it, which saves having to wire the class across from the unbundle to the bundle when I want to update the data. Normally, I'd recommend always using a named unbundler, but with this simple position cluster, I'll use the compact unbundler since I know it's always row then column, and it aligns nicely with index terminals. Then, to check a specific position, another in-place element structure can be used with an index array border node to get the individual Boolean element. The value that comes out of the left border node will be what the Boolean value was previously, and then, since the square is asking about it being safe to move, I'll always mark it as becoming occupied. The right side of the in-place bundler also needs to be wired up. Finally, the safe terminal can be wired up, although the Boolean will need to be negated with a not node, since the caller cares whether or not the position is safe, but the array is storing whether or not the position is unsafe. Now that the logic for this VI is completed, it's time for one last feng shui pass on it. The strategy that I'll be implementing is squares always replicate to the north when safe, otherwise they move west when that's safe. Now let's get the new team VI I just created wired up in the squares run VI. I've already placed the position utility sub-VI that returns the square's current position, but I'll need to determine the desired position adjacent to the square to use with the team VI. This can be done with the resolve direction position utility sub-VI that takes a starting position and a direction. The board wraps around edges in SquareBattle, so the board size also needs to be passed into the sub-VI so it can wrap positions properly. As stated, the square will always want to replicate north first, so I'll specify that direction with the enumeration constant. The correct position is now available to use with the team sub-VI. I'll use the safe output of the sub-VI with a K structure to replicate if it's true or do something different if it's false. With the safe direction known, the replicate utility sub-VI can be used to create the run result cluster value. For this simple square, a copy of the existing square can be used for the new square. This true case is done, and the team class needs to be wired across. However, I now have two copies of the same constant value, so I should wire to the outside constant, which will let me tweak directions in a single location. If it was not safe to replicate to the north, now the square can check if it's safe to move to the west. I'm going to use the square position and board size values I've already retrieved, along with another copy of the position utility sub-VI. This will be nearly identical, but with a direction of west instead of north. Again, I can use the team's sub-VI to check this new position to see if this west position is still safe to move to. I need to make room for another K structure based on this sub-VI's output. I also know I won't need the team class anymore, so I'll wire that across both cases. In the true case, meaning that it is safe to move west, I can use the move utility sub-VI to create the run result value, which only needs the direction. Then in the false case, since it is neither safe to the north nor west, I'll just let the square wait. As mentioned, there are a few issues with this first attempt, but let's see what it looks like to run this square. Since I'm only testing my team, I can decrease the board size for better visibility. I left the number of rounds it takes to replicate at the default of 50, so we get to watch me click like mad to get to the 50th round. Both squares will be able to take actions again, and I'm naively expecting the top square to replicate north and the bottom square to move to the west. Uh-oh. It almost looks like the top square moves north and the bottom square does nothing. Since the logic is simple enough, I know that's not the case, and what actually happened is that the top square replicated further north, and the bottom square replicated over the existing square, resulting in them being eliminated due to the collision. This isn't the behavior I wanted, so let's get that fixed up. The problem is that I'm reinitializing the unsafe position array every round, and it needs to remember where squares are located each round, so that will not work. Instead, I should initialize the unsafe position array once at the start of a game, and let it be reused each round. The logic in the new round VI is no longer needed. A sub-VI for the team will be needed, so squares can update the map when they are no longer at a position. This will be very similar to the check mark unsafe sub-VI from earlier, but will instead always set the value at the position to false since it is no longer unsafe. Since it is so similar, I'll just copy and paste the logic from the other sub-VI to start out. I can then change the value to false and the output is not needed. Without needing the value from the left border node, this inner structure can be exchanged for a replace array subset node. I'm done with the logic, so it's feng shui time again. Let's not forget that every good sub-VI has a unique icon. With this sub-VI, squares can now let the team know what positions have become safe. The first instance of this is whenever a square is moving to a new position and the old position becomes empty. Time to test again, and this time I'll lower the number of rounds a square spends replicating to test faster. With the first round, the replication happens the same as before. After the replication, the bottom square now moves to the left as it properly saw that the replicated square was still present. On the round after moving, the square that moved has an opening to the north so it replicates again. This properly continues, creating a growing triangle of squares. Now that my desired behavior is working, let's add a second team and see what I may have forgotten to account for. After I restart LabVIEW because I realized the app is bugged out and isn't listing the team I already added. This happens occasionally when stopping a match for some reason, and eventually I'll release a bug fix. With the project open again, now I can test my team against itself. And ignore that the teams aren't displaying again. They do show up properly during a match. The game now has more than one team with active squares and I can let it free run. I'd expect the blue team to continue expanding into the space where it's eliminating green due to collisions, however the team is still showing these positions as unsafe since I've only marked positions safe when a square moves. Positions also need to be marked safe when a square is eliminated due to a collision or from being attacked. The square class already contains the VIs that need to contain this logic. These three VIs are run by the engine when the corresponding event has happened, just like how the team class has its game and round VIs. The team map can be updated in the collision and attacked VIs to mark positions safe where squares were eliminated from. This is as simple as calling the mark safe sub-VI from the team with the square's position at the time it's eliminated. I can get the position sub-VI from the right-click palette menu with the square's wire. I'm going to skip showing editing the attacked VI since it will be identical. Test time again, and this time let's also see how the team fares against a different team. This Galaxy team utilizes the coordinated movement example from earlier to great effect. Yeah, this isn't going well for my team. As you can see, having the ability to spread out is crucial. Let's remove the Galaxy team now that my team has been obliterated, and at least see how my logic fixes I wanted to make panned out. Green is continuing to expand into the space where it's colliding with blue, but it looks like nothing is happening where blue has run into green. Blue is in fact occasionally eliminating a green square via collision, but then green immediately replicates to fill the space. It's finally time to use the remaining action and have squares attack opponents that show up next to them. Attacking opponents that are visible to a square is easy, but will require adding some room to the left side of the diagram. Since the rest of this logic won't change, I'll also tidy it up so it needs less space. The disable structures that contain the utility VIs are still at the bottom, so I'll bring them back into view. The VI I'm interested in is the Find Enemy sub-VI that returns all the directions around the square that currently have an opponent. If the returned array is empty, that means no directions have an enemy adjacent to the square and the existing replication and movement logic can be run. Conversely, if the array is not empty, then I'll just take the first enemy direction listed and attack there. This uses the attack utility sub-VI and uses an index array node to pull out the first direction. Let's see how this runs one last time now that all the actions have been demonstrated. Now we can see that blue is able to slowly eat into green as it moves west and then a green comes into range that it can attack. Comparing this simple team against the Galaxy team from earlier, something to keep in mind is that squares that are completely surrounded by their own team are nice and protected for a bit, but become effectively useless against opponents and have no room to continue replicating. This results in very slow growth. Congratulations! You made it to the end of this video. If you'd like to ask any questions about this competition and to discuss strategies with other players, be sure to check out the Summer of LabVIEW Discord server invite link in the video description. The SquareBattle channels in the Discord server will have all the announcements and deadlines for this year's competition, so you'll also be able to keep up to date with any bug fixes and news about the competition. We look forward to seeing what behaviors you come up with for your teams and hope you have fun with this challenge.